In this session, we're going to cover all of the spectroscopy that is required. That's mass spectroscopy and infrared spectroscopy. You should already know from Module 1 how the mass spectrometer works, but we're going to recap it anyway. So, there are 4 stages in a mass spectrometer that you need to worry about. Ionization, acceleration, deflection, and detection. Typically, you can get up to 8 marks for knowing those 4 words and 1 line about each. So ionization happens when high energy electrons from an electron gun bombard the sample and remove an electron. Acceleration is where the charged particle is accelerated towards negatively charged plates. Deflection is where the particle stream changes direction as a result of an electromagnet. And finally, detection is where the positive ion hits a negatively charged plate and causes a current.
Wowzers.
Right. Now we're going to move on to Module 2, mass spectrometry. Start off with the molecule. It gets ionized, and what you end up with is a molecular ion. Okay? It's lost 1 electron, but that electron has come from a pair. Okay? If you think about it, even something as simple as water has got 8 electrons in the outer shell of the oxygen, but they're in pairs, 2 bond pairs and 2 lone pairs. The moment you remove 1 of those electrons, you've got an unpaired electron, and you've also got a positive ion. And so what this symbol here means, this plus and this dot, plus means it's an ion, and the dot means it's a radical. Does that make sense? So the molecular ion is an ion and it's a radical. After that, what can then happen is the molecule splits up. And you can get a radical and an ion, or in this case, a radical and an ion. You get different splitting occurring depending on where the molecule has lost an electron. Does that make sense? Yeah. Is the radical going to be accelerated? No, because it's not positively charged. So if this molecule splits up here, you're just going to see this appear. Whereas this one here, you'll only see that appear. If this has got a mass of, say, 100, this is going to have a mass of less than 100, because some part of it is broken off and formed a radical. Does that make sense? Good. You can then sometimes get further rearrangement of fragmentation, and it's only the positive bits that actually get detected. In Module 1, you only have to worry about elements. In Module 2, you have to worry about the organic species, okay, and organic molecules and how they get broken up. But importantly, only the bits with a positive charge get detected. So, few points. The highest M over Z value usually corresponds to the molecular ion. Okay, at this stage, you can assume that the furthest peak to the right-hand side, that's your whole molecule. And everything short of that is fragments of the molecule. So the furthest one to the right-hand side tells you the molecular mass of the substance. Happy with that? The tallest peaks come from the most stable species. What you do get, is a typical fragmentation pattern for a molecule. And so it is possible to identify the molecule from the sorts of fragments that it forms when you put it into a mass spectrometer. Position of the peaks, differences between the height of the peaks and so on is to do with the stability of the ions, tells you what the molecule is. So here we've got a mass spectrum. And this one's got molecular ion 144. Now I told you the furthest peak to the right-hand side, that's the whole molecule, yes? Is that the furthest peak to the right-hand side?
No.
No, there's one next to it. There's an eeny weeny little one there, just there. Anyone know what that one's caused by? This is an organic compound, and about 1% of carbon that occurs naturally is not carbon-12, it's carbon-13. And this peak here is where one of the atoms is not carbon-12, it's carbon-13, and so it's got an increased mass of 1. This is still the molecular ion, and that's your carbon-13 molecular ion. But we've then got a load of other peaks. Okay, this is C8H18. So let's look at, say, this big old peak here. This is a peak at maybe 43, something like that. Mass spectra for organic molecules is all about the 12 times table. Can somebody please divide 43 by 12 and give me a remainder? You can do it in your head. 43 divided by 12 is what remainder what? 3 remainder 7. 3 lots of 12 is 36. Okay? 43 is 3 remainder 7. Let's think about that for a minute. CH3, CH2, CH2. 3 carbons, 7 hydrogens. Did that just make sense? 43 divided by 12 is 3 remainder 7. 3 carbons, 7 hydrogens. CH3, CH2, CH2. This is what? 57? Yeah? What's that going to be then? C4H9. After that it gets a little bit trickier because say it's 71. So 71's okay. What's that? C5H11. After that it gets a bit complicated. So 85 is not 7 carbons and 1 hydrogen. It's 6 carbons and 13 hydrogens. Yes? You all know your 12 times table, don't you?
No.
12, 24, 36, 48, 54, 60, 72, 84, 96, 108, so on. Did I say 54? 48, 60, 72. I jumped into my 9 times table there. Never mind. So, molecular ion, molecular plus 1 ion. Here are your different peaks. 29, okay, C2H5, C3H7, C4H9, C5H11, C6H13, C8H14. And there you have them there. Oh dear, we've got this word again, carbocation. That just means carbon positive ion. Okay, happy with that? And so on. This bit, you're unlikely to get examined on this, but you should know that a more stable, in this context, a more stable carbocation is a tertiary carbocation, and so on. Okay, just like we looked at with the organic mechanisms, tertiary carbocation is more stable than a secondary carbocation. So, if we look at halogenoalkanes, if you were to put in C2H5Br, you're going to get 2 Br peaks, 79 and 81, because those are 2 isotopes of bromine. And you're then going to get loads of other stuff. And oh look, peak at 29, C2H5. So you put in C2H5Br, there's your Br, there's your C2H5. Actually, these 2 peaks here, those aren't Br on their own. What are they? What are these 2 peaks here? Yeah, they are the whole molecule, but with the 2 different bromines. The bromines themselves are here. No, they're not. They're here. Okay? Whereas these are the whole molecule with the two different bromines. Does that make sense? Okay. On this molecule here, there are two ways that it can split relative to C double bond O. Nice and quiet, please. If it splits along this line here, then you get the carbon, the R dash, and the oxygen, which means the colour coding on this slide is actually incorrect. All right. If those three, okay, are together, then you're going to get that fragment. Notice R just means the rest of the molecule, and to distinguish between two different rests of the molecule, we use R and R dash. So, if you break along the blue line, for some reason you have to follow the red arrow and you get that fragment. If you break along the red line, okay, then the R, the C, and the O are together and you get that fragment. Okay? Excellent. If that's my molecular ion to begin with, and there's my charge, okay, and there's my unpaired electron, we could break it up and you get this. You could, if you got this one, okay, you would also get some of this. Okay?
Ow, sorry.
This one doesn't get accelerated because it's a radical. That one doesn't get accelerated because it's a radical. Okay? If you can just go round.
Go down, please. Go down.
Alternatively, you can get that one, okay, or that one. And at this stage, you don't need to worry about any preferences. Okay? Can you just pause for a second?
Yeah, man.
At this level, you don't have to worry about which one's going to be formed in a higher abundance or not. Okay? So all I want you to realise is that if you break the bond in different places, you get different fragment ions. Some are more stable than others, some will appear at a higher abundance than others. Now, if you do have oxygen in your molecule, okay, you've probably got a molecular formula, something like that, okay? You then have to subtract 16 before doing your 12 times table analysis. Put it simply, 43 minus 16, I'm making the primary rule of breaking the primary rule of public speaking, just trying to do mental arithmetic while speaking. 43 minus 16. 27. 27 divided by 12, okay? 2 remainder 3. Happy with that? Okay, and so on and so forth. Here, we're not going to spend too much time on there. We've got a double peak there. We've got peak 7981. What does that mean we've got? Bromine, molecular ion of 122 or 124. So, let's say 79. 122 minus 79 is?
69.
I don't know, I'm really not doing it. Go on, you've got a calculator. 122 minus 79 is? 43. 43 divided by 12 is 3, remainder
7.
What's this molecule? Name of it? Bromopropane. And so on and so forth. And I'm not going to go through those. Right, small break and then we're going to move on.
Adam's answer's back.
Okay, there are 3 things that you need to remember about infrared spectroscopy. Okay, if you remember nothing else about it, remember these 3 things. 1, the peaks, you look up on the table given to you at the front of the exam and they tell you what functional group it is. 2, if you ever get breathalyzed, it's an infrared spectrophotometer, and what they're really looking for is an OH peak. Okay? That's how a breathalyzer works. And 3 is the reaction between infrared light, or the absorption of infrared light in the C double bond O that causes carbon dioxide to be a greenhouse gas. If all else fails, remember those 3 things. 1, the peaks tell you the group because it's in the front of your booklet and you don't need to remember any of the numbers. 2, breathalyzers look for an OH peak. And 3, okay, the greenhouse effect is actually linked in to this. Now let's do it in a whole heap more detail. So, infrared spectroscopy works on the fact that when bonds vibrate or stretch or whatever, they can absorb some infrared light. And there are all sorts of different stretches, wobblings and so on that can take place. So this is called symmetric stretching, and this is where, okay, molecule moving backwards and forwards, and a certain type of infrared light will make the oxygen molecule do that a bit more. Then you've got asymmetric stretching, and a certain frequency of infrared light makes water do that. Then you've got bending. Yep, absolutely. This is aerobics chemistry, and a certain frequency of infrared light is going to make the molecule do that. Very simply, and you don't really need to know this for an exam. Light is generated. It is split into two beams. One beam is your reference beam. The other beam goes through your sample. Your sample absorbs some frequencies of infrared light. Nice and quiet, please. And you're able to compare the absorption of your sample with the reference beams. You happy with that? So, this is the water molecule, and it's quite happy. There it is. It's vibrating. And there's the water molecule after it's had the infrared light shone on it. Okay? It makes it vibrate more. Happy with that? And we're going to come back to that because I really want to just skip on until I find one. Here is a spectrum. And we have lots of different frequencies. You're not required to remember any of the numbers. You get a table of data. It's at the front of your exam. And there are two ways you can identify what the compound is. And this is really what the slide 2 previous was saying. One is you can look at what's called the fingerprint region. And this is pretty much unique for any molecule. I've only seen one exam question ever ask you to do this. And all it did was give you 3 different fingerprint regions and ask you to match 2 of them. Okay? I genuinely could have given it to my 4-year-old and he could have done it. You do need to know that a fingerprint region is pretty much unique to any molecule, and by comparing your unknown sample with a reference, with a large number of fingerprint regions, a computer can identify what the sample is just from the fingerprint region. Does that make sense? However, should you end up being an organic chemist and you synthesize a new molecule, you can't look it up, okay, or a hideously complicated one. And what you have to do is look at the different peaks and try and work out what it contains. Now, this little peak here, okay, is going to have, it is due, I think, to a CC bond. Okay, there's some peaks that I know the numbers of, and there's some that I don't. Whereas this peak here is due to CH bonds. Different bonds have different absorptions. And what this really is, because this is absorbance, here it's absorbed 100% of the light, but at that very specific frequency it's absorbed about 90% of the light going through. Whereas here, none of the light has been absorbed. Does that make sense? You understand the principles of it? Okay? This one here, this is absolutely classic. Okay? This is C double bond O, carbonyl compound. Okay? Very sharp peak, somewhere around the 1700 mark, C double bond O. And you'll see that in aldehydes, ketones, esters, carboxylic acids, acyl chlorides, and amides. They all have a peak about there. Here is your alcohol peak. And this is a great big broad stretch, okay, broad OH peak around the 3000 mark. Okay? Now, breathalyzer doesn't produce something like this. It's just looking specifically at that frequency. And should there be large amounts of alcohol in your breath and you were caught behind the wheel, at that point the policeman gets a bit nasty. Not happened to me. I've been breathalyzed once, okay, and there was no alcohol on my breath. Which was pretty much good because I'd made the cardinal sin of crashing my car in a country I didn't speak the language, and got breathalyzed shortly after crashing the car. And if they found alcohol on my breath at that point, they'd have been in a lot of trouble. So, this is the OH peak. It's how breathalyzers work. This is a more complicated one. This is a carboxylic acid. There's your C double bond O peak. And there's your OH peak. This bit here, that's a CH peak. This is an ester, so there's your C double bond O. But notice, no OH. Carboxylic acid, OH, ester, no OH. Okay? So immediately you can tell the difference between two isomers. If you've got one molecular formula and you're told one isomer is a carboxylic acid and the other is an ester, given spectra, you should be able to work out which it is. So, whoops, overshot. OH stretch, alcohol. C double bond O stretch, aldehyde. OH stretch and C double bond OH stretch, sorry, C double bond O stretch, carboxylic acid. You are not required to remember these numbers. You are required to be able to look them up in the table of data at the front. And here is a very large table, which you are not required to know. Okay? And that really is it. Okay? But I said something about the greenhouse effect, didn't I? C double bond O. Okay? The C double bond O absorbs infrared light, but not visible light. Which means the visible light from space can come through the atmosphere, heat up the Earth then radiates back infrared light, which doesn't get through the carbon dioxide. Hence the greenhouse effect. Does that make sense? So, if all else fails, identify the peaks using the information at the front of your exam. Breathalyzers and the greenhouse effect are both linked into infrared spectroscopy. Are we happy with that?
Yes, boy.
And that's infrared spectroscopy. Okay. Ollie?
Yes.